everyone, welcome to part 3 of chapter 20. Today we are going to wrap up our chapter on radioactivity and nuclear chemistry. This lecture is all about applications of nuclear chemistry. So we're going to look at fission, we're going to look at fusion, we'll look at how radioactivity affects us biologically, and then we'll look at some other uses of radiation. So here we go. So today we are looking at non-radioactive nuclear changes. So changes that are happening to the nucleus that are not because of radioactive decay. So two main things here, fission and fusion. Okay, so in fission, we have nuclei that are really, really large and they're really unstable, right? Usually because of this neutron to proton ratio that we talked about last time. Or they just may have greater than 83 protons in their nucleus. But so they're really unstable. And so if you hit their nucleus just right with a neutron, then that big giant nucleus will split into two smaller nuclei. And when that happens, it's going to create really large amounts of energy in this reaction like you see to the left here. In fusion, we have small nuclei that are essentially, slammed together to make a larger nucleus. Okay, so in fission, we have a large one breaking apart, and in fusion, we have two small ones that are fusing together to make a large nucleus. Either way, both of these processes, both fission and fusion, release huge amounts of energy. But fusion does actually release more energy per gram than fission, and we'll look at that a little bit later. So let's do a little bit of history. Today's lecture actually has quite a bit of history in it, but it's because it's interesting. So back in the 1930s, Enrico Fermi found that bombarding uranium, right? Remember, uranium is the heaviest element that we have at this time. So his plan was to bombard uranium with neutrons and try and make a big element, right? He was trying to essentially expand the periodic table. Can I make an element that's larger than uranium? So what he was hoping that he could convert some of these neutrons that he was, pounding uranium with, and he was hoping that they would undergo beta decay and turn into protons, therefore increasing the atomic number. So that was the plan. So he took his uranium, hit it with a bunch of neutrons, and he saw that beta decay was happening. And so he hypothesized, hey, I think maybe I've made bigger elements, right? But again, whenever we're doing chemistry, a lot of times it's hard to figure out what you've made, right? Unless you go through and analyze the products, because you're not really, usually it's not a visible change, especially on the atomic level like we're talking here. So he never actually went and looked at the products, so he wasn't sure really what he had produced. So these three researchers took over his research, or kind of picked up where he left off, and they again went and took some uranium and bombarded it with neutrons. They also saw the beta decay that was happening, but instead of the beta decay being due to making a larger element like he hoped, it was actually that he was creating smaller elements. He created barium, which is much smaller than uranium. So Meitner realized that the unstable uranium nucleus was being split by that neutron's impact. So this was the discovery of nuclear fission, okay? So he didn't end up making these larger elements, he ended up making smaller ones. So here's what happens. So this is our uranium atom, and we're going to hit it with a neutron. So here's our neutron here. And when the neutron hits this uranium, it causes it to split into barium, krypton, and 3 neutrons, and it also releases a lot of energy. Like I talked about earlier, fission reactions produce large amounts of energy. Okay, so again, instead of this undergoing beta decay and turning that neutron into a proton, it undergoes beta decay for sure, right? But it is splitting the atom and it's producing these 3 neutrons, which are going to be important in a minute here. Okay, so we notice that it took 1 neutron to start this fission process, 1 neutron to start, but we ended up with 3 at the end. Okay, so this signals that this can be a chain reaction. This is a self-amplifying reaction, right? Because 1 neutron hits a uranium and creates 3 neutrons. So if each one of those 3 neutrons that are produced hits another uranium atom, and each one of those produces 3 more, right? Now we've got 9. And so this is what's called a self-amplifying reaction, because it gets bigger and bigger as it goes. It's a chain reaction because a reactant is also a part of the product of this whole process. Okay, so uranium, the uranium here that we're looking at is uranium-235. This is a fissionable isotope because it produces barium and krypton. We're not going to get into, your book talks about it a little bit. We're not going to get into which isotopes are fissionable or not. We're just going to look at uranium-235 for the level of this class. Okay, but if we had some natural uranium, it's less than 1% uranium-235. Most of it is uranium-238, but it's not fissionable. It doesn't break into these products like uranium-235 does. So, but if we just had natural uranium and we started, we hit it with a neutron, the likelihood that we're going to hit one of those uranium-235s is pretty low, right? 1%. And then those 3 neutrons would have to go and find, 3 other uranium-235s that are nearby. So there's not enough uranium-235 in natural uranium to sustain the chain reaction to make it really useful. So to produce fissionable uranium that can have this chain reaction, we have to enrich our natural uranium. And so depending on what we're using it for, you'll have to enrich it to different levels. So if you were to make it a weapon, right, if we had, a nuclear bomb, then you would need it to be 7% because it's a very fast chain reaction. But if you just needed it for a nuclear reactor and we actually control that reaction, then you would just need about 3%. Okay, the minimum amount of a fissionable isotope needed to sustain the chain reaction is called the critical mass, because we would obviously mass this out because we have different masses of these isotopes here. So here we go, fission chain reaction. So our 1 neutron will hit our 1 uranium-235, and it will cause 3 neutrons to split, like I was talking about. Each one of those will hit another uranium-235 and cause each one of those to split. But again, it needs to be hitting a fissionable isotope, so we need to have enough of it present to sustain the chain reaction. So all of this research was taking place during World War II, and those 3 scientists that we were just talking about that developed fission or discovered fission, they were German scientists. And so some of the US scientists feared that Nazi Germany was going to develop a bomb that was based on this nuclear fission, because we saw it can, it's being produced by a chain reaction and it creates a ton of energy. So this could have really catastrophic results. So Einstein, right? So all of these scientists convinced Einstein to write a letter to President Roosevelt, which is what's shown here, to warn him of the possibility of, Germany creating a bomb. So Roosevelt was like, okay, let's set up a committee to start researching, all these atomic reactions, all this nuclear chemistry. And fun fact, he actually didn't allow Einstein to join the team because he feared that he could be a spy, because he's actually from Germany. So one of the greatest minds of the time didn't get to work on this project simply because he had been from Germany before. So kind of a bummer, but still majorly successful project. In 1941, they began it. It was called the Manhattan Project. It was top secret and super, super expensive. The primary goal was to build an atomic bomb before the Germans did, right? So they were on a clock. So the project was led by this physicist down here in the bottom right. His name was J.R. Oppenheimer, and it was the project took place in Los Alamos, New Mexico. So you've likely heard of the Manhattan Project if you took a world history course maybe in high school. So over those 4 years, they did a ton of work, and on July 16, 1945, the United States detonated the world's first nuclear weapon at a test site in New Mexico. And Oppenheimer said, "I am become death, the destroyer of worlds," right? As he watched that very first atomic explosion. So this was before, obviously we were using them in the war, before any of that. This was the very, very first explosion, the very first nuclear bomb, but they showed that this fission process could be weaponized. So the whole point of this project was to essentially beat the Germans to make an atomic bomb before they did. But ironically, the Germans didn't make any successful nuclear bombs at all. They didn't really make much progress, and they had already been defeated by the time the United States was able to weaponize this nuclear fission. Germany surrendered on May 7th, and our bomb was detonated on July 16th. So again, it was kind of close, but it was already over. So they decided, the United States decided to use these atomic bombs in the war, and they created 2 more from this Manhattan Project, and they named them the Little Boy and the Fat Man. So they dropped Little Boy on Hiroshima on August 6th, and then the Fat Man on August 9th, and those effectively ended the war, right? Japan surrendered shortly thereafter. Together, these two bombs killed approximately 200,000 people. These are major reactions. Okay, these are not the small scale chemical reactions we are doing in class. These are very large scale nuclear reactions. There are tons of energy produced in this fission process. So somebody finally realized, hey, nuclear fission generates a lot of energy, right? What if we could slow it down and capture this energy to be used to generate electricity? In a nuclear bomb, all of this energy is released all at once. But what if we could slow down that chain reaction? What if we could moderate it somehow so that we could get the energy coming out when we want it to and be able to make it useful for us? So now nuclear energy generates about 20% of US electricity and about 70% of electricity in other countries. So we're definitely behind here. And they use the fission of uranium-235 to produce this heat. And then the heat boils the water, which turns it to steam. The steam turns some turbines, which generate electricity. So here's that all. So this is the reactor here. The reactor is where the uranium-235 is being hit with the neutrons, right, in that chain reaction. And we can control the speed of the chain reaction using these control rods that we're going to talk about on the next slide. This is all wrapped in a big containment shell to make sure that nothing goes bad, right? Nothing goes wrong. And we'll talk about that again in a minute here. And then, there's, this has like a safety protector around it. And then this is our containment shell here. It's usually made of concrete and it's really thick. This is our steam generator, right? This makes heat, and then the heat makes steam. The steam can turn this turbine, and then we can get electrical output from the generator. Super cool, super clean way of producing energy. And I think it's a much better use of this fission process than these atomic bombs. So let's talk about the core of the fission reaction. So that's this here, okay? So the core has all of the fissionable material. This is about 3.5% uranium-235 because, again, we don't need it to be we don't need it to have a ton of uranium-235 because we are going to control the speed of the reaction. If we put in too much uranium-235, then our reaction is going to go too fast, and then we would get too much energy at once, and obviously that would be unsafe. So we want lower amounts of uranium-235, enough to sustain the chain reaction at the speed we want it to go, but not so much that it's going to blow up the power plant. So they're stored in these really long tubes. They're called fuel rods, and they're arranged in a matrix. And then between all of these fuel rods, we have the control rods, and they can go up and down. Okay, the control rods are what control the speed of the reaction. They're made of neutron-absorbing material because remember, the neutrons are what causes the chain reaction to keep going, right? And so if we put something in there that can absorb the extra neutrons or absorb the neutrons that are going when we don't want them to, then we can control the speed of the chain reaction. So these tend to be made of boron or cadmium, and they can either insert or retract in here. So I'll look at this. So these are the control rods here. Okay, so they can go up and down essentially, and so they can block the neutrons from hitting more uranium-235, or you can open it up and make it go faster, right? So they can insert them or retract them to control the amount of neutrons present, which controls the rate of the fission reaction. This allows for controlled chain reactions to occur below the critical mass, which is really awesome. So we don't need to use quite as much. And because we can control the rate of the reaction, we can control the amount of heat that's being produced and therefore the amount of electricity being generated. Okay, it's not like more heat makes more electricity, right? If we have too much heat, then our nuclear reactor can't cool down well enough, and that's where we get into problems, as we'll see on the next slide. If something were to go wrong, if there was a power failure, right? This whole thing runs on electricity, but if there was a power failure, then those control rods will automatically drop straight down into the fuel rod assembly, and it shuts down the whole reactor. Okay, so there are a lot of safeguards in place to make nuclear power plants really safe now. And again, I'll talk about when they weren't safe in just a minute here. But here's benefits of nuclear versus coal burning. So a nuclear power plant uses about 50 kilograms of fuel to generate enough electricity for 1 million people. That's awesome, right? And there's no air pollution. We know that coal burning is associated with a ton of air pollution. It produces nitrates and sulfates and all kinds of things that add to acid rain, which causes a lot of harmful effects in the environment, in addition to degrading, marble and things like that. It also produces carbon dioxide, which adds to the greenhouse effect, which is impacting global warming, right? And coal burning is not very efficient. We need 2 million kilograms to generate enough electricity for 1 million people. Okay, so 50 versus 2 million, that's a big difference. Okay, so nuclear has a lot of benefits. It's, a much cleaner process, it's a much more efficient process, and it's better for the environment. So why don't we all just switch to nuclear, right? And I'm guessing most of you know the answer to that. People are scared. People are worried something bad is going to happen, and, likely for really good reason, because we've seen it happen. If there is water that's lost from the core, okay, so we have water that's going through the core and is continually cooling it down. Okay, the fission process releases a lot of energy, and so it gets really, really hot, really fast. So we need to keep it cool to keep that reaction going at a pace that we can control. But if the water is lost from the core, then the reaction can overheat, and then it can melt the core, and then we would get an uncontrolled reaction. Okay, we would get the fission process would just kind of go at whatever speed it wants to go. So one example of when this happened is Chernobyl, and you've likely heard of this before. If you haven't, there are lots of documentaries on it, and I highly recommend watching them. I am not a documentary person by any stretch of the imagination, but watching documentaries on Chernobyl is really interesting because it is still not inhabitable. Okay, the nuclear power plant there exploded in 1986, and people still cannot live there today. It's crazy. So if you're at all interested in that, I would, check it out. But what happened is that in this, nuclear power plant, there were, a bunch of safety features, and they intentionally disabled them. They went through and shut them all off because they were doing an experiment to figure out if they could reduce their maintenance costs. Okay, they had really high maintenance cost, wanted it to be cheaper. So they were like, hey, let's try this thing out, turn off some safety features, and didn't go well. Right? It exploded, and a bunch of people died, and a bunch of other people were impacted by the effects of radiation. So everyone that lived, in Chernobyl and in the surrounding areas had to leave and never come back. Okay, so it is still completely deserted. It was an epic disaster, but I want to be really, really clear here. This was not a nuclear detonation. It was not the explosion like you think of when you see, the nuclear bombs. It is not a nuclear bomb. A nuclear power plant cannot become a nuclear bomb. The uranium fuel does not have enough uranium-235 to produce a nuclear detonation. Remember, we were looking at it has about 3.5%, and a nuclear bomb has about 7%. It has double the amount of uranium-235, so that's how we get the bombs. This cannot turn into a nuclear bomb, but it can cause some major devastation, especially just, in that power plant itself, and obviously in the surrounding area if it went really, really poorly. But I want to be really clear. U.S. nuclear power plants have additional safety features to produce accidents happening like this. So if you live, near a nuclear power plant, or you're trying to decide, should you be pro or con nuclear power, I want to be really clear that we have a lot of safeguards in place so things like this do not happen. Obviously, accidents will still occur. So like in Japan in 2011, an earthquake triggered a tsunami. Okay, the tsunami flooded the power plant, and it caused the cooling system pumps to fail. Okay, and so when they failed, things overheated, and we had a partial meltdown of the fuel. But there were no deaths associated with this accident. Okay, or with the radiation from this accident. Okay, so even though the cooling pumps failed, and it was devastating, it wasn't Chernobyl. It wasn't this catastrophic nuclear explosion. Okay, so people, though, are still really worried about jumping on board with nuclear power because they're afraid that Chernobyl will happen, right? If they said, hey, let's take out the Viselium Mall and instead we're going to put a nuclear power plant there. Is everybody cool with that? Everyone's great? And most people would be like, no, I don't want to live next to a nuclear power plant, right? What if something happens? So we can go on and on and on about how safe they are, how, things have been double checked, triple checked, it will be fine. And people still say, no, think about Chernobyl. So even though science has come a long way since then, and, we're not going to go through and intentionally disable any safeguards, right? People still have this idea that nuclear power is unsafe. So we're fighting against that, even though there's all these benefits of nuclear power, and it would be really beneficial. We're still fighting against this mindset that nuclear power is unsafe. So they're also not just, that they're unsafe, but we have a problem with nuclear power waste disposal. Okay, so the waste that comes out of this is still really radioactive. Okay, and so we can't just put it in a landfill, right? Because it's radioactive. So we have to store it somewhere where it's not going to cause damage to the people nearby. So right now it's stored on site, and it's stored usually in, concrete containment. Sometimes it's stored underground so that it can be protected from, anyone around it. Okay. They were going through and developing a permanent waste disposal site in Nevada, but in 2010, the Obama administration halted all of that, and they said, hey, let's look at other alternatives. They wanted to look at temporary above-ground storage facilities, permanent underground facilities, so they're still working on all of this. So all of this is still a work in progress. This is things that are happening now, but hopefully we will eventually make the shift to nuclear power, because that would solve a lot of problems with energy and efficiency and all of that. So where does the energy in fission come from, right? I told you it produces really large amounts of energy, but why? Right? Well, during nuclear fission, some of the mass of the nucleus, of that original nucleus, is converted into energy. So when we go and we hit, uranium-235, let's say, with a neutron and it splits, some of that mass is not going to be accounted for in the new nuclei. Okay, some of the mass, essentially disappears. But it doesn't disappear. It is, turned into energy from this equation, E equals mc squared. So the difference in the mass between the separate nuclei and the combined nuclei is called the mass defect. Okay, and again, we can use that mass difference. The mass difference is going to be pretty small, right? But it's times the speed of light squared, and that will get us our energy that's being released in this reaction. And if you do this enough times, right, you're going to get a ton of energy that's being produced. Each mole of uranium-235 that fission produces about 1.7 times 10 to the 13th joules of energy. That's a ton of energy, right? If we think about in class a really exothermic chemical reaction, one that would be like really exothermic, that would be about 10 to the 6 joules per mole. So this is like a crazy amount of energy. So here it is. I want to be clear, I'm not going to make you know how to do the math on this. We've done a lot of math in this class, but I would like you to understand where the math is coming from to help us understand why fission produces so much energy. So if we look at the mass of our reactants, so we have our uranium-235 and a neutron. So when that neutron hits the uranium-235 and splits it, we're going to get some barium and krypton and 3 neutrons like we were talking about earlier. But if we add up the masses of all of those things, our mass here does not equal our mass of the stuff that we started with, right? And we know, right, mass cannot be created or destroyed. So where did it go? Well, it was turned into energy. So we can go through and we can calculate the amount of mass lost in AMUs. Then we can convert our AMUs into kilograms. Remember, AMUs stands for atomic mass unit. So that would be the mass of like one atom. We'll convert that to kilograms to make it easier to work with, and so that we can do math with it. And then we can plug it into our, E equals mc squared. So we'll do our mass in kilograms times the speed of light squared, and we'll get our joules. And so this is our joules per atom. All right, now let's go ahead and switch gears and talk about fusion. So fusion you can think of as being the opposite essentially of fission. Fission, we talked about one really large nucleus that was splitting into two or more pieces. Fusion is when we combine small nuclei to make a really heavy, more stable nuclide. Okay, so this is the reaction that's taking place in the sun. It's taking place in other stars, and they're using the fusion of hydrogen isotopes to make helium. And that process, that cramming together those hydrogen nuclei to make helium, releases a ton of energy. Okay, it actually produces 10 times the energy per gram that fission does. Okay, so it's like, whoa, you thought fission produced a lot of energy? Just wait till you look at fusion. Okay, but this process requires extremely high input of energy and really high temperatures in order to initiate the process. Because if you think about the nucleus of a hydrogen atom, right, there's a proton in there. There might be a neutron or two depending on the isotope, but there's one proton in there. And then if you wanted to find another isotope of hydrogen, there's still one proton in there. And in fusion, we are cramming together those two nuclei. Okay, well, if you have a positive and a positive, they're not going to want to sit next to each other, right? So this process requires a ton of energy because we need to overcome that force of repulsion in order to make those nuclei stick together. So it requires a ton of energy to make it go. However, lots of benefits. There are no radioactive byproducts like there are in fission, right? Fission, we have a big problem of dealing with the waste. Fusion, you don't. You make helium, which is actually would be really helpful because the world is short on helium. But the problem is that we don't have any materials that can withstand high enough temperatures in order to house this reaction. So even if we could make it go, it's going to melt whatever container we put it in as we try to slam those hydrogen atoms together. We don't have a facility on Earth that can replicate the sun, so this is kind of a problem. So even though it has a lot of benefits, we can't make it happen. Currently, the amount of energy that we need to put in to make the fusion reaction happen, even if we can do it, is so great. We have to input so much energy that the amount of energy that we're getting out is actually less than the amount that we're putting in. So it doesn't make sense for us to try and use this as a viable energy source. Okay, right now, the only working application of fusion is the hydrogen bomb, which is unfortunate. So here is the reaction for fusion, and we'll see this again on the next slide. This is tritium. This is an isotope of hydrogen. This is tritium, an isotope of hydrogen that has 2 neutrons and 1 proton, so it has a mass of 3. And then this is deuterium. It is an isotope of hydrogen that has 1 neutron and 1 proton, so it has a mass of 2. Okay, and so when we cram these isotopes of hydrogen together under really immense pressure and heat, we can get a helium, which has 2 protons and those 2 neutrons, and then it will release a neutron in this reaction. Okay, let's talk about transmutation. So we talked about transmutation a little bit before. Transmutation is just when we have one atom of one element is turned into an atom of a different element via a nuclear reaction. So when we were talking about this before, we were looking at it because of radioactive decay, right? It underwent beta decay or alpha decay, and it had a different number of protons. Therefore, it became a different atom. Okay, so now we're going to look at artificial transmutation. Okay, so when scientists in a lab are causing new elements to be produced. So the way that we do this is we have we take our elements and we accelerate them. We make them have a ton of energy and go at really high speeds. And when they're at, have a lot of energy, they're at really high speeds, we slam them into each other. Sometimes we can produce new, heavier nuclei. Okay, the particles can be radiation from other, a radionuclide like neutrons or protons or things like that. But more commonly, these are just particles that we are accelerating and then we are slamming into each other in order to make a larger nucleus. Okay, this is actually how most of the elements after uranium were made on the periodic table. Those are not naturally occurring elements. Those are elements that we've made in a lab and they have a really, really short half-life. So it's like we slam the elements together. We're like, ah, did you see it? Did you see it? Oh, there it was, I made it, right? And so we have, obviously ways of measuring these elements, but that's more how they were produced, okay? They were produced using these really high energy accelerators. So we're gonna look at those. But here's an example of the reaction. So this is uranium-238 and carbon-12, which is a really common isotope of carbon. And if you slam those together, right, you can get, this is not right, sorry. I'm like, not oxygen. Californium-244, and some neutrons, okay? And again, this is being made in a particle accelerator. This was made in a particle accelerator at Berkeley, which is why it was named Californium. So here is one example of a particle accelerator. This is a linear accelerator, and so we have a charged particle, like a proton, that's going in one side, and it's going in an evacuated tube. So the whole thing is under vacuum. There's no air. There's nothing in there. And then we have a potential difference from one side to the other with an alternating voltage source usually, depending on the type of application, but we're having a voltage applied across it. And since this proton is positively charged, right, it will respond to the voltage, and we can cause it to increase in velocity as it travels through the tube. This is a multi-stage, this picture here is a multi-stage linear accelerator, and the one in this picture is at Stanford. Okay, so this is the Stanford Linear Accelerator. But the way that it does it, there's different sized tubes here. And when the proton is leaving one of the tubes, that tube will end up being positively charged. So it repels the proton after it leaves. And then the next tube is going to be negatively charged so that the proton is attracted to it and kind of speeds up as it goes. And so it will keep alternating positive, negative, as it keeps going, which will cause that proton to continue to move faster and faster and faster and faster and faster as it travels down this tube until it hits the target down at the end. And the target can be, whatever we're trying to slam it into in order to make a larger atom. So another way that we can do this, instead of having a linear tube, because this takes up, as you can see, this takes up a lot of space, right? Sometimes they will do a cyclotron. So they'll do the same kind of thing, but they will put it in in a circle. And what happens is we'll have our proton source in the middle here, and then as it goes, it will travel out and out and out. And the two sides, right, you can see one side's kind of a lighter gray and one side's kind of a darker gray. So instead of doing like in the linear one where we had, the positive charge as it was leaving and the negative charge as it was approaching, the cyclotron will alternate the sides of this circle and will be, one side will be positive, the side that's leaving, and the side that it's approaching will be negative, and it will switch back and forth. And so it will cause the electron or the proton to go in a circle. And there's also a bunch of magnets that are making sure that it goes in a circle like that. And it will keep picking up speed as it goes until it exits, exits and hits our target. Okay. Again, this is allowing scientists to make larger and larger and larger elements that don't exist in nature. Since they're elements that are larger than uranium, we call them transuranium elements. Anyways, this is the Fermi National Accelerator Lab. This is in Illinois. All right. I want to do some practice problems here just so we can look at how we would write reactions for these processes. Okay, it's the same kind of idea that we were using before when we were looking at alpha decay and beta decay and electron capture and positron emission. It's the same sort of thing. All the same rules apply. The numbers on the top, right, the mass numbers have to be equal on each side of the reaction, and the numbers on the bottom, the atomic numbers, have to be equal on each side of the reaction. So I want you to see if you can go ahead, try these out, solve these problems, and come back when you're ready. All right, let's try this out. So the first one, we are bombarding nickel-60 with a proton to make cobalt-57. Okay, so we'll need to figure out what else is being made in that process. So here we have nickel 60, so our mass number is 60. And then we have an atomic number of 28 because that's nickel's atomic number on the periodic table, and it's being hit with a proton. So you could either write this as H or you could have written this as P+. Either one is fine. And so our numbers on the top have to be equal. So it's telling us we're making cobalt 57. So we know this is a 57, this is cobalt, and that's 27 because it's cobalt. So the numbers on the top on the left add up to 61, so this has to be a 4. The numbers on the bottom add up to 29, so this has to be a 2, which makes this helium. All right, let's try the next one. So bombarding nitrogen 14 with a neutron to make carbon 12. Okay, so again, we have 14 and 7 because this is nitrogen, and we're adding a neutron. We make carbon 12. So if we add up the numbers on the top, we get 15. That means this needs to be a 3 on the top. And then the numbers on the bottom add up to 7, so this needs to be a 1 on the bottom, which tells us that this is hydrogen. So this is tritium, one of the isotopes of hydrogen. And then last one, bombarding californium-250 with boron 11, which produces 4 neutrons and something else. So again, add up the numbers on the top, right? So we're getting 261. So we're getting 4 1s here, which means that this has to be 257 in order to add up to 261. And then we're getting 103 on the bottom, so we need 103 on the bottom here, which gives us lawrencium. All right, last little bit, I want to talk about the effects of radiation. Okay, so we've talked about before a little bit that ionizing radiation can be harmful, right? Ionizing radiation has really, really, really high energy. And so it can knock some electrons off of different molecules, and it can also break bonds in your body. So these can be really, really bad, right? Because your cells have now been damaged. And a lot of times, your body can go through and repair these damaged cells, but not always, and not always fast enough. And so if it can't repair the damage to the cell, then it can cause malfunctions, and that's where you get into trouble. So there are 3 different types of radiation effects. So one is acute radiation damage. We have another one that is increased cancer risk, and then finally different genetic effects. So acute effects of radiation would be if you got hit with a really high level of radiation over a short period of time. So this would be like if you lived in Chernobyl, right, when the explosion happened. That would be a very acute, you've got hit with a lot of energy in a very short amount of time, which can be really, really harmful because it will go through and it will just kill a large number of cells all at once. And this can cause either a weakened immune system, or it can simply cause you to die. It can cause you to die instantaneously, or if you get hit with enough of it and it damages a bunch of cells, that can cause an infection and then you can die from that. So you want to obviously not be exposed to a nuclear bomb or to a nuclear reactor core. Either one of those, bad news. More commonly, though, you may be exposed to low doses of radiation over an extended period of time. Okay, and that would give you an increased risk for cancer. Okay, and again, this is because radiation is damaging your DNA. It's damaging your cells, and they either may not get repaired in a timely fashion, or they may not get repaired the right way, and they may be, malformed. Okay, so these changes in DNA can cause your cells to grow abnormally, and any abnormal growth can become cancerous. Okay, it's actually, though, hard for us to pinpoint whether cancer, whether you've gotten cancer from radiation or you've gotten cancer from some other thing, because cancer is actually fairly common. So it's hard for us to pinpoint, you were exposed to this, therefore you got cancer. So even though we know this to be true, we actually have a hard time proving it. Low doses over time may also damage reproductive organs, right? Because again, this radiation, this ionizing radiation is damaging your cells. So it could damage your reproductive organs, which can then lead to sterilization. So no more kids. It can also do damage to some of your reproductive cells, and it can cause to genetic defects in the offspring. They haven't actually seen this in people, but it has been observed in lab animals. So they do hypothesize that it could be true, although, likely uncommon. So here's just some ways that you may be exposed to radiation. So we have 2 different kinds. really. We have natural radiation, which is, things that you're exposed to all the time. So if you went on an airplane, you'll get some radiation. You're also getting some radiation all the time from outer space. You may have, you have some natural radionuclides in your body. That gives you some radiation. And we talked about radon gas before. Like I said, commonly a problem back east. You may be exposed to that. Okay. There are, radiation that you're exposed to, via medicine, which is why you don't necessarily, anytime they want to x-ray you, you want to really evaluate, do you want to be x-rayed or do you need to be x-rayed? Okay. A chest x-ray, not very much. Dental x-rays are more, and especially if you do the dental x-rays with the two bite wings, that's even more. But again, there's some of these, like a CT scan, that's a lot of radiation. And again, you want to keep your total radiation count down, to minimize your damage to your cells, essentially. Okay, so here, on average, each adult is exposed to about 310 millirem. Oh, sorry, that's what I wanted to point out to you. These doses, and it talks a lot about dosing in your books. We're not going to get into those calculations in this class, but these doses are in millirems. Okay, so 1/1000th of a rem. These here are rems. So I just wanted to make sure that you're noticing the difference there. Okay, so these are when it says 20 here, it's 20,000 of the previous slide. But on average, each adult is exposed to about 310 millirem of radiation per year from natural sources. So that's not including any medical procedures. That's just, if there was, radon in your basement, or, you were taking an airplane ride, or you wore a watch, or, whatever the case may be. If you, have a bunch of medical procedures that are being done that use radiation, obviously this number would be higher. Okay. These are, this is where you start to get into problems, right? If you get above about 20,000 millirem or 20 rem, then you start to see decreased white blood cell count, which indicates that you may have a risk of developing cancer. If it gets higher, then you can get radiation sickness and things like that. And obviously too much radiation and you would die. So keep your radiation count down. But again, I'm not saying this to scare you. I'm just saying this to make you aware that there is radiation that you are exposed to all the time, in addition to the radiation that you may experience at the doctor's office or the hospital. So radiation can be really bad for you, but radiation can be really helpful. Obviously, if doctors are using it, it can't be all bad, right? So we can use things that are called radio tracers that can be absorbed by your body. So a lot of times it may be something that you drink. Like if you were going to do a barium enema, you might drink a bunch of barium, and we can track where it's moving in your body to look at different organs. We can look at your bones, right? This one here is a bone scan. They're using gamma ray emissions from technetium-99. So they have different radioisotopes that they use for different purposes, because those radioisotopes will gather in different parts of your body and allow us to see what's happening in there. Okay. When we have isotopes like this, we call them tagged isotopes because they are radioisotopes that we can scan and we can measure. They're usually radioisotopes with a really short half-life, so they're not going to be in there very long. You're not going to walk around glowing for a really long time. And we also use isotopes that are low ionizing. So this would be beta or gamma. Remember, we talked about alpha decay is like a semi-truck, essentially. It can do a lot of damage, but you're usually protected from that by, wearing clothes or having your skin. But if you drink something with alpha decay, that could be really, really harmful. Okay, so we want to use a radioisotope that's low ionizing, like beta or gamma decay. And again, scans like this one, like this bone scan, are used to locate cancer most often. This bone scan can tell us if there is cancer in the bones that has, spread from somewhere else in the body. Because the bone scan of someone with cancer in their bones is going to look different than the bone scan of of someone with no cancer. So, conversely, we also use radiation as a treatment for cancer. So after we've been talking about this, you should think, well, why is that, right? That should be really harmful. That should be like a bad idea. Why would you want to get hit with gamma rays? That's going to give you more cancer, right? Well, radiation kills cells. Okay, radiation kills cells, but it kills the most rapidly dividing cells the most, if that makes sense, right? It's going to go and target the ones that divide the fastest. And cancer cells divide really, 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 really fast, which makes them more sensitive to radiation than healthy cells. Okay, so we can use this targeted radiation. So this is a gamma ray treatment for someone with cancer. We can use targeted radiation to kill the cancer cells without doing really significant damage to the healthy cells, because the radiation will kind of selectively target those cancer cells over the healthy cells. The person undergoing this radiation treatment, though, will still, may still get some burns on their arms, or, may experience hair loss from the exposure to the radiation. But the chance that it could work greatly outweighs the harmful effects in this case. And then finally, we also use radiation, not for medicine, we use it for other things, right? So one of the ways that we use it is we can sterilize medical devices by killing microorganisms. So again, when we hit them with, ionizing radiation, that will go through and kill some of those microorganisms that may be living on medical devices or living on your food. We can use radiation to kill bacteria, we can use it to kill parasites, and I don't want you to be alarmed. By hitting your food with radiation, we do not make the food radioactive. It just goes in and kills all the bad stuff on it. It doesn't affect the nutritional value of the food whatsoever. It's just used to make it safer and make sure there's no weird bugs, essentially. We can also use radiation for insect control. Again, ionizing radiation, we can use that to hit things like fruit flies, and we can sterilize like the male fruit flies and then release them out out into the orchard or wherever the case may be. And when the female fruit flies mate with the male fruit flies, then there's no offspring being produced, and that can control the insect population. We can also use it to authenticate old art objects. So a lot of older, pigments and ceramics were made from minerals that have small amounts of radioisotopes. So we can use, things that measure radiation to determine whether that's an authentic painting or not. And then finally, we can also use it in nonstick pan coatings. A lot of nonstick pan coatings are polymer reactions, and so we'll use things like UV light to start the polymer reaction to make like the Teflon coating on your nonstick pan. That is really interesting if you don't know much about it, but we don't have time to get into polymer reactions right now in this class. But that is it for our chapter on nuclear chemistry and radioactive decay. We've covered a lot of ground in this chapter in kind of a small amount of time, but I hope you thought it was interesting. I know I really did. Today we talked about fission and fusion. We talked about uses for each, kind of benefits for both, and some of the downsides for both. Then we looked at particle accelerators and saw how we can make larger elements. And then finally, we looked at some of the uses of radiation and also some of the harm that could befall you if you experience too much radiation. So that's it for today's lecture. Make sure you are working through those problems on this chapter, right? Because you need to go through and review all of those kinetics and writing those nuclear reactions, and make sure you are solid on that because the final is rapidly approaching. So keep working hard. As always, if you have any questions, please send them my way, and I will talk to you guys next time.